This work performed with my former PhD student, Vijay Nagaraju, who's now assistant professor of computer science at the University of Tulsa, and two of my undergraduate students. This work performed under a supplement to the National Science Foundation grant I have. And I'll explain what that long title means. This is not so much about DevOps, but modern software practices. Key takeaways are that DevOps is not this thing you get in a box. It's a set of practices. And colloquially, the goal is to reduce system development lifecycle time while preserving quality. So I went after this as a way to get into quantitative modeling because it's just quality talk. Not very gratifying for people who want to do quantitative assessments. In that regard, you get dozens or hundreds of papers promising you DevOps is the next greatest thing as sliced bread, but not really showing you how to measure and execute on those promises. So in this regard, there are very few formal models. We tried to develop one initial one, and it's very back of the envelope, but it was fun to do, especially with undergraduates just getting their hands on modeling and the related topics. In that regard, this is a definition taken from a very popular textbook that is very accessible. That's by one of the Australian research groups, CISRO. And so here I'll read you the full definition. It's DevOps, they define as a set of practices intended to reduce the time between committing a change to that system and then that change being placed into operation. So this is what they call functionalities. And you can clearly see there's a process performance metric to this, as well as ensuring quality, whatever that means. Maybe it's reliability, maybe it's safety, maybe it's security, or whatever you think you need to measure for your software processes and the systems it goes into. So what we've done is just play around. This is just an academic model. Maybe it could grow into something, maybe it's no good at all. But we've attempted to define process and product metrics. So process metrics would be delivery time. Product metrics would be all those things I just described. And ultimately, what we're trying to do is give it a quantitative basis from my core area of expertise in software reliability engineering, also into cybersecurity, test and evaluation now, as well as resilience engineering, but going back to the fundamentals here. And what it gives rise to is a very interesting problem, which we will eventually use. So really this whole talk is about the problem enumeration, not actually the solution. We have begun to work on the solution, but what it gives rise to is this multi-objective problem. I have to trade off delivery time if I want to get no security leaks, for example. All right, we got to go slow and we got to find this under test with a smaller set of, and of course there might be technical capabilities to accelerate. So really what we're looking at is a kind of accelerated life testing in the software testing domain is what I would characterize it as. So we're going to look at two trades, which is delivery time versus downtime, and I've defined some very simple back of the envelope metrics for that, and essentially gives a way to assess. Now here, simple observation. Big organizations that have global operations, Facebook, Google, LinkedIn, these big social media sites, they don't just make a change and say, here, everybody use this. What happens if it causes like the whole system to crash? And it happens occasionally. It's in the news, and it's a massive inconvenience and bad PR, right? So what we did was, I'm glad I'm talking to the slide you're actually seeing, not the next one. But so we came up with this notion. So site reliability engineering is Google's term for what they do when they incrementally deploy a product. So you got a state model, you have dev and ops, all right. And then there's something in between called the incremental deployment stage. And the idea here is that the population being exposed to that software, who can then fail it, is increasing. So there's a monotonic increase. But what's also happening, I'm going to step over here quickly. I'm sorry for people online. I better stay over here. But the lambda transitions back to the dev state indicate the rate of failure. So the further states to the right, the higher the failure rate, because there's a larger population, just monkeys on keyboards that are going to crash software. That's how it's going to be. And so we can think of the trade-off, it's implicit in the structure of the model. The farther we go to the right, the faster we're speeding up the timeline of finding the defects, but the consequences will also be greater. More people get that same crash, or more people have that same bad thing happen, whatever it might be. So obviously there's a trade-off, intuitive. So here's just the visualization of the timeline of some defects discovered. So again, this is not data from like what they call DevOps and telemetry and all that good stuff. It might be multiple timelines of smaller sets of defects being discovered. But what we're looking at here is the notion that the defects, there are many simple superficial defects being discovered earlier on, and that as time goes on, they're further spaced out, meaning that maybe we could speed things up and things wouldn't be so bad. That's the intuition. So a whole bunch of numbers, just notional for the sake, and it's going to impact the metrics. So I'll show you like two policies. Neither are optimal, but they give you a sense that, all right, so we just say in the end state, that final state ops, there's 10,000 users. The middle state will only have 10% of the population, meaning that there will be 100 or 1,000 users in that middle state, and that the dev team is just 50 people. They're the developers, making very simple back of the envelope. And then we're even making this totally, and I'm going to trash it before people attack me for it, ratio of acceleration factors. So, if there's 1,000 users, they're not all as good as those testers who know how to attack their own software, obviously. So this is a really painfully academic exercise in modeling the acceleration factor that future research could collect the data and know better. Is that really the factor, or how good are the testers at? And so these numbers are just for the notional sake. We define delivery time as the time to get to the end of that timeline with all those defects, plus the time to go from the first state to the end state to remain in the op state. So it just sounds good. We got through all the bugs. We worked out all the bugs, and now it's operational. Again, there can be so many flaws in the modeling, but trying to do something simple, we just use one intermediate state. We took the metrics we defined as, say, we have a mean time to repair. Say you have the developer crashing their code versus 1,000 people crashing their code versus 10,000 people crashing their code. And yes, there might be some additional coefficients, but depending on what state you were in when you hit one of those defects in that timeline, add that up. That's the overall distributed. That's a population metric of all the unhappiness you caused to the people who are using your software at the time. So if there are more people, you would have a larger number. The unhappiness factor with the defect would be proportional to how many unlucky people had that. And maybe not everybody has that unlucky experience. On the right-hand side, so there's this interesting ranking. So the subscript C, S, and TS on the dollar signs. There was an really old Oak Ridge study characterizing, this is totally, just shows you how badly we need to rework the value of data and systems in general, but they classified the penalties for loss of classified data at various levels. That was my 7 minutes.
You've got 2 minutes.
Great. All right. So I may still succeed. I might prove you wrong. Better shut up. So Oak Ridge did a study. This was building K25. It was like nuclear material decades ago. But the idea was that losing top secret data was 100 times as bad. I think that's just not a realistic quantification. But sure, let's just use it for the sake. So depending on whether we were in the op state and we leaked, oh gosh, that's really bad. That's a penalty of 100 versus leaking in the interior state where, oh, something top secret got leaked to all these people who didn't need to know, but we can somehow contain it and there's a cost to it, better, right? So we really need to do a better job there. So re-showing you, I'm probably not gonna live up to my promise, I'm sorry, but that little state model in the top right, and you can see on the timeline, so we go top policy, 35 units. So it's simple time-based policy. We try to rush and we get at time step 3, we fail. We stay in that initial dev state. Another 30 seconds, we stay in the dev state because we fail. So, but after 35 seconds, we go to that gray bar in the middle. So we're now in the intermediate I state. And so you can imagine that this is just showing which state we're in as a function of time. And there are 2 policies here. One is more conservative. It takes longer to transition from the dev state to the I state. So it's more conservative. And you can see that the metrics on the bottom lead to less downtime because we have less crashes at the later stages. And like I said, those numbers gives a Pareto curve. You see some traits like this. We're just brute force enumerating policies with different combinations of transition times from dev to I and I to ops. This gives rise to a problem of reinforcement learning. What is the optimal policy? And can we, in real time, make a decision to decide which state should we be in? Could we actually throttle it back? So that's where, like I said, we've applied various techniques from reinforcement learning to solve that problem. We also did some sensitivity analysis, and we showed that the bad metric, your delivery time or your downtime gets worse along the transition from the dev state to the incremental deployment state, because that's where you're increasing the risk the most by rushing. And then we did a 3-dimensional study. So you have red, green, or whatever those colors are. Red means the highest severity. This was safety data from NASA, not classification levels, but the concept and abstraction holds. And you see this 3-dimensional Pareto curve. The idea is that can we get that reinforcement learning algorithm to get flush with the brute force enumeration there? So you can see the knee in the curve is 3-dimensional. And if we want to get low downtime and low safety or security violations, we need to be there in the curve. And how do we figure out the shape of that curve without even knowing? So those are some of the research challenges. And I guess I'll stop there because everything else is not so interesting. Hope I made it.